Good evening, ladies and gentlemen. On behalf of the Rector of the University of Seville, Miguel Ángel Castro, I would like to welcome you to the induction ceremony of the Nobel Prize laureate, Professor Robert Hoover, to the Royal Academy of Sciences of Seville. Our Rector does apologize for not being able to be with us. He would very much have liked doing so, both as a Rector and also as a Professor of Chemistry. Our deep gratitude to the Council of Economy and Knowledge of the Andalusia government, Professor Antonio Ramírez de Arellano, for his presence in this special day. Thank you very much, Antonio, for being one more time with us at the University of Seville, your home university. Thank you very much also to the Academy for choosing our main hall, the Paraninfo, for this annual ceremony. Emeritus Professor José Luis de Justo Alpañez, President of the Academy of Sciences of Sevilla, the floor is yours.
Va a dar comienzo el acto de presentación como académico de honor de esta Real Academia del Dr. Robert Hoover, propuesto estatutariamente en Junta General Extraordinaria de 20 de abril de 2016. El señor secretario va a dar lectura de la parte del acta de dicha Junta en la que se aprobó la propuesta.
En el acta de la Junta General Extraordinaria de la Real Academia Sevillana de Ciencias, celebrada el 20 de abril de 2016, figura como punto tercero: elección si procede de un académico de honor. Se presenta una candidatura firmada por los 6 presidentes de las distintas secciones de la Academia, a favor del profesor Robert Hoover. El presidente de la Academia da la palabra al ilustrísimo señor don Miguel Ángel de la Rosa Acosta para que exponga ante la Junta los méritos que concurren en el candidato. Tras la exposición de estos méritos se procede a votación secreta de la propuesta. Dicha votación produjo el siguiente resultado: votos favorables 28, no se registraron votos en contra, ni en blanco ni nulos. En consecuencia, el excelentísimo señor don Robert Hoover adquirió la condición de académico de honor de la Real Academia Sevillana de Ciencias.
Tiene la palabra el ilustrísimo señor don Miguel Ángel de la Rosa Acosta para pronunciar el laudatio de presentación del nuevo académico.
Consejero de Economía y Conocimiento de la Junta de Andalucía, vicerrectora, presidente de la Real Academia Sevillana de Ciencias, presidente del Instituto de Academias de Andalucía, señores académicos, colegas, dear friends, colleagues and participants at the Biointeractomics Workshop. It's a great pleasure and an honor for me to be here today to address and to deliver this laudatio in the honor of Professor Robert Hoover. Professor Robert Hoover was awarded the Nobel Prize in Chemistry in the year 1988, along with other 2 German colleagues, Weissenhofer and Hartmut Mickel, for solving the 3-dimensional structure of a photosynthetic reaction center from bacteria. This was the first time that protein complexes embedded in a biological membrane was solved. The most difficult achievement was just really to get the crystals to solve the structure of this membrane complex, and this is the main reason, the major achievement of this time, some years ago. So after that, Professor Robert Hoover has been following a very productive scientific career, and he has got a lot of long list of nominations and recognitions, and you can see here he has been, for instance, appointed Doctor Honoris Causa in Belgium in 1987, and then by the University of Ljubljana in Slovenia, the Universidad Tor Vergata, Roma in Italy, Universidad Nova de Lisboa in Portugal, Universidad Autónoma de Barcelona in Spain, Tsinghua University in Peking, Beijing in China, Nagoya University in Japan, Universidad de Buenos Aires in Argentina, Universitas Vilnius Vilnius in Lithuania, Bulgarian Academy of Sciences in Sofia in Bulgaria, and the Jagiellonian University in Krakow in Poland. He has also received a lot of awards and distinctions from many societies, and this is some of the major honors that he was receiving from some of these societies, like Honorary Member of the American Society of Biological Chemists, Honorary Member of the Swedish Society for Biophysics, Honorary Member of the Japanese Biochemical Society, Member of the European Academy of Arts, Science and Humanities, Member of the Accademia Nazionale del Liceo in Rome, Member of the Orden pour le Mérite für Wissenschaften und Künste, Foreign Associate for the National Academy of Sciences in use in the United States, Fellow of the American Academy of Microbiology, Foreign Members of the Royal Society in London, or Honorary Member of the Spanish Society for Biochemistry and Molecular Biology. In this context, I would like to just to mention that Professor Robert Hoover has been very closely related to the Spanish biochemistry for many, many, many years, and for this reason he was recognized by the Spanish Biochemical Society. So another awards you can see here: Otto Warburg Medal, Kaelin Medal from the Biochemical Society in London, Cone Award from UK, Sir Hans Krebs Medal from the Federation of European Biochemical Societies, the Linus Pauling Medal, Max Tixel Prize from the Harvard University in the United States, and also I would like to mention and to highlight here Honorary Professor and Visiting Professor in the university, in the University in Seville. Actually, she will be the third time that Professor Robert Hoover will be lecturing here in this Paraninfo, in this room. So you can see this is a picture with the rector, the former rector of our university when he was nominated honorary professor in 2008. And this is in the magazine of the University of Seville. But he has been related to our city for many, many years. This is the first time, maybe you recognize yourself. It's difficult for me to recognize myself. But anyway, so this is the first time that Robert Hoover was here in the University of Seville in 1997, almost 20 years ago. This was because of the workshop from the European Science Foundation organized here in Seville, and the topic was molecular recognition in metalloproteins. This lady you can see here is the former city mayor. So this is a resection on the city hall of our city in Seville. So later on, Robert Hoover was coming back to Seville with the occasion of this symposium supported by the Aristide Foundation on metals in biology and medicine. It was in 2005. And it was just the starting point for a long-standing collaboration with our scientific research center in Isla de la Cartujas. Because after that, Professor Robert Hoover was coming every year, 1 week in May, just to teach and to lecture to the PhD students. And this is a PhD program we were running along with other universities in Spain. Actually, this was an inter-university PhD program in collaboration with the University of Barcelona, Zaragoza, and the National Research Council in Madrid, and our university. And so he was here just not only lecturing to the students, but also giving and addressing a lot of lectures at different places, in different institutions. Here, this was with the Royal Academy of Sciences, the same like here today. And in collaboration with the Aristide Foundation, we were just organizing a meeting on the membranes, interfaces, and surfaces. And Robert was just lecturing, was one of the lecturers in this, on this occasion. This is a very nice picture when you were here in 2007, sorry. We were visiting the German school, and I would like to say that today the director of the German school is here with us, also was inviting, and so he's attending this session. This was when we were visiting the the National Accelerator Center, and you can recognize here our consejero, our Minister of Sciences and Economy in the Andalusian government, when he was Vice Rector for Scientific Research in our university. And the guy there on the left is the rector. He's not with us. And so I have to say that they both, the consejero and the rector, they are both members of our Institute of Material Science in the Cartuja Center. And this is also in 2009, visiting the facilities of our university and also the School of Chemistry. And this was in 2010 on the occasion of the workshop on transient molecular interactions in biology. This is during the round table. And in 2011, it was quite interesting, this meeting we were organizing. It was actually a breakfast. A breakfast with some business people from our city. And the topic for this session was just on renewable energies. Maybe you remember. Just talking about the use of different sources of energy for the future. And so this was the heading, the title of the journal of the newspaper the following day. So we cannot, or we should not, cover a fertile land, a fertile country, with solar panels. It was a message, was quite hard in this time because in 2011 there was a lot of investments, a lot of money just for solar energy. So it was not so easy to say that when you have just when you have in front of you an audience that all people were just investing money in solar energy. So it was with some academicians, just Robert Hoover talking with Benito Valdez, who was the former president of the Royal Academy of Sciences, and Professor Garcia Novo, who was vice president. And this was in 2012, with the occasion of the International Congress of Biochemistry and Molecular Biology we were organizing here. This was the first time that this Congress was in Spain, in particular in Seville. It was the Congress of the International Union of Biochemistry and Molecular Biology, and along with the European Federation of Biochemical Societies. So Robert was one of the lecturers on this occasion, and this was also one of the sessions that Robert Hoover was so kind to participate. This was a meeting with the Nobel laureates attending the Congress. And you can recognize here, from left to right, Professor Farid Murad, Ada Yona, Hamilton Smith, Robert Hoover, and Venki Ramakrishnan. We were just sitting all of them together to talk about investment in science. And science as a motor for economy, is a driving force for the economy in the future in modern societies. So it was the most important message we were transmitting there to the people in the audience. And here in the audience, you can see it was very close to this place in the Hotel Alfonso XIII. And you can see here, sitting on the first row, the current president of the Academy of Sciences. But in addition to all these official, between brackets, official meetings or sessions, Robert Hoover he likes just to discuss and to interact with young people. And this is the last time, the last picture I'm going to show you, just to highlight this aspect of Professor Hoover. This was some years ago in Puerto Varas, Puerto Montt in Chile, and this was an excursion. He was organizer with some PhD students from Chile, just to spend a day with all of them visiting the volcans. This was just visiting the lakes and the volcans, and to interact with them along the whole day. And I remember now when one of the times, the first time he was here in our institute talking to the PhD student because of this PhD program, he was giving the lecture, the opening lecture, the first session, the first day, Monday morning, and there was a lot of scientists, researchers from our center that they would like to attend, to follow the lecture of Professor Huber. And the room was completely crowded. But after that, when he finished, he was asking all the professors, all the teachers to get out of the room because he wanted to be only with the 25 students because we were inhibiting them. So it was really very, very funny, and so we appreciate very much all this participation, interaction of Robert Huber with the young people. And well, this is just to finish and to highlight the reason why he received the Nobel Prize. This is one of the most important reactions in living world, which is just how plants, all the photosynthetic organisms, are able to capture, to get the light energy, and to transform, to convert into chemical energy. So this is a photosynthetic reaction center. You can see all the chlorophyll molecules like antenna, just getting all the light, the photons, to excite the chlorophyll molecules and to start to trigger all the molecular reactions inside the plant cells. So this is the structure they were solving. This is a protein complex with many different subunits. It's a very large macromolecular structure, and they were solving, Professor Huber, along with Disenhofer and Mikkel, they were solving the structure of this protein, which is embedded into the lipid membrane in bacteria, in photosynthetic bacteria and plants. And so, just to summarize at the end, Professor Huber has been working not only in photosynthesis, his field of research is mainly structural biology, and he has been interested in many different aspects from the structural point of view with many biological systems. Just to summarize, he has been working on the proteins of energy and electron transport, like in photosynthesis, but also on proteases and their natural synthetic inhibitors, metalloenzymes, with metals like iron, nickel, molybdenum, copper, and some others, proteins of the immune system, antibodies and antibody receptors, protein hormones and their receptors, protein kinases, proteins of cofactor and vitamin biosynthesis, and many others. And also some important contributions to the methodological developments. For instance, the development of Patterson methods in crystallography, methods for structural determination of protein complexes by nuclear magnetic resonance, synthesis and use of electron-rich metal clusters, crystal annealing and improvement, methods and instruments, and analysis of targets in pharmacology and crop science. So this is a whole life devoted to science with a great success. So I have to say, just to finalize, saying that this is again a great pleasure and an honor for me to be here today to address these words in the honor of Professor Robert Huber. So welcome to your academy, to the Academy of Sciences in Seville. Thank you.
Thank you, Dr. De La Rosa. Now, Dr. Robert Huber has the floor for the introductory speech in this academy.
Honorable President, I wanted to greet also the Rector Magnificus, but unfortunately he cannot be here, and I would wish him a quick recovery from his accident. Honorable Consejero, it's a pleasure to see you here again. And dear Miguel, I was moved actually to listen to you describing our long-standing relationships. A pleasure. to hear that again. Now, I'm very much honored to be accepted as honorary member of this famous Real Academia Sevillana de Ciencias, and being in the midst of outstanding scientists and personalities. Pleasure. Now, I'm in Seville to enjoy this event, and I have the pleasure to see this city in May, where it shows its nicest side, the flowering jacaranda, and then away further out the countryside, the blooming meadows. It looks as if somebody put a mix of colors on earth, and then the white villages around. It's really beautiful, Andalusia, at this time of the year. But I'm also here to attend the exciting FEPS IUBMB workshop and conference on biointeratomics. Thank you for the invitation. Now, life is about interactions of atoms with atoms to form molecules, molecules with molecules to form complexes and molecular machines in cells, and cells interacting with cells to form organs, and organs interacting with organs in a living human being. And of course, humans interacting with humans in our societies, in a conference, in the academia. So it's all about interactions, and I'm happy to be a member of the Academia Sevillana. Now, my lecture is about seeing. And vision is actually, of course, a fundamental prerequisite for understanding of interactions at any level. And we are very fortunate right now to live in a century where incredible progress in our capability to see has been achieved. We learn to make use of the very wide spectrum of electromagnetic radiation, 12 orders of magnitude. So from gamma rays to radio waves. We learn to make use of this wide spectrum for imaging. And what you see, the top of this, the upper part of this slide is we learn to image whole bodies, organs, cells, and molecules. Now, what I would like to do is just to highlight and to give you a few glimpses of the, of the incredible progress that we had in the last few decades. I first start with super resolution fluorescence microscopy. Now, the problem with optical microscopy is that there is a strict physical limit of resolution, which was first formulated by the physician and optician Ernst AB, saying that the maximum resolution that one can get with optical light is half wavelengths. So if you work with light of 500 nanometer, then the limit is a resolution of 250 nanometer, which of course is insufficient to see molecules, or of course entirely insufficient to see and resolve atoms. Now, in the last 10 years, people have found a trick to navigate around AB. AB's law is not broken, but you can navigate around. And what do they do? Now, the example I show is a system of 8 light-emitting objects, too close together to be resolved in an optical microscope. So what you see here in a conventional fluorescence image is a smear, giving some kind of idea of the shape of this object. Now the trick these researchers have found, which were honored with a Nobel Prize in 2014, was to introduce time in the sense that each of these 8 emitting components lights up at a different time. And so that only one of these is visible at a particular time. And of course, then AB plays no role, and you can, in principle, define the position of this single emitter with unlimited precision. It just depends on the number of quanta that you count. So these are intelligent tricks these people used, and they helped us very much in biology. Well, this is an example of super resolution microscopy where you have the individual emitters lighting up at different times, and you have to collect thousands and 10,000s of different images and then get a high resolution picture of this object. Another glimpse on the development of electron microscopy. Now, electron microscopes were designed and made in 1930 by Ernst Ruska, and they meant enormous progress compared to light microscopy. But in the last 10 or 15 years, people learned to achieve atomic resolution images of biological materials using modern electron microscopes. Mainly it is due to the novel detectors and novel electron lenses and preparation procedures. So what you do is you take an image of 10,000s or so of this biological object, and you wouldn't believe at first sight, if you look at the original image, that you are able to analyze these to discover the atomic structure, but actually you are, by taking thousands of these images, looking at the molecules. Then a critical step is to orient them in identical ways, and in that ways you reduce the noise, and you are actually able to get a high resolution, atomically resolved image of these molecules. A wonderful progress in electron microscopy just in the last 10 or 15 years. Well, NMR is not an imaging technique, it's a spectroscopic technique, but again, we learned in the last 20 or 30 years to make use of it for structure determination, because the method gives us information about distances of nuclei, and by a triangulation from these information we can determine three-dimensional structures. As a spectroscopic technique, it, in addition to structural information, gives us also ideas about the dynamics. So this is a unique property of NMR, structure and dynamics. Now, of course, I come to my own field of methods in structural biology, which is X-ray crystallography, and this brings me more than 100 years back. The critical event was in 1912, when the German physicist Max von Laue, who worked in Munich at the university, discovered X-ray diffraction by crystals. So what you see here is the birth document of X-ray crystallography. Not a nice picture, smeared reflections, but they showed the fact that X-rays are electromagnetic radiation, crystals are regular lattices, and then this can be used for structure determination, as you will see in a minute. This, by the way, is Laue at one of these Lindau conferences where every year Nobel laureates are coming together to speak to students. Usually 40 or 50 Nobel laureates from different fields meet 500 to 600 students. So I just can recommend to the students to apply and try to find a place there. It's a unique opportunity for them to see these guys from which they read in textbooks, living. Well, these are the founding fathers of X-ray crystallography, protein crystallography. This is Röntgen, who discovered the X-rays, Laue, who discovered X-ray diffraction. Now, the discovery of X-ray diffraction by Laue was spread very quickly in the scientific community, and within a few weeks or so, the Braggs, father and son Bragg, working in Cambridge, England, heard about it and drew the right conclusion that this would be a method to determine crystal structures, simple ones, sodium chloride, for structure determination. They founded a school in Cambridge, England, where Max Perutz worked and began to consider crystallographic analysis of protein crystals. He is the father of protein crystallography because he found a method how to decipher the complex diffraction patterns of proteins and to determine phases. I have no time to talk about that. Well, growth of biological crystallography. Now, I entered the field in the late 60s, and it was less than a handful of protein structures that were known at that time, 4 or 5. I was a very young guy at that time and was happy to work in a field where there was no competition. All you do, whatever you did was new. I mean, nobody else had worked on that before. Now, slow progress over many years until about 1990, and then you see this exponential growth in the analysis of protein crystal structures. And that is due to technological advances. Bill mentioned a few. The fact that understanding biology requires to see the molecules, and then lastly, the application in medicine. I come back to that towards the end of my presentation. Well, a few words about my institute, which was opened in 1972. I was offered the directorial position there. You see an institute in the forest. And actually some called it Martin's Rue. But it was nice to be there. Now, the campus in Martinsried has changed. This was the institute you just saw. As another Max Planck Institute has been added, an innovation center, an incubator has been added, and many university institutes have settled at the campus. It's now a campus with about 10,000 people there. Very important to have a large group of scientists from different disciplines together, very fertile. Well, so what was the reason for this exponential growth that I mentioned of protein crystal structure determination? One, of course, was the fact that we now have recombinant proteins, we have crystallization robots. All of these were not available when I started in the late 60s. We only had natural protein material available and required large amounts, by the way. Now, we have these strong X-ray sources, the synchrotrons. This is one of them. In Spain, you have the ALBA, and we are very well off in Europe with almost a dozen of different synchrotrons in the relatively close space, close distance. Now, this is the Hamburg Synchrotron. This is, for a comparison, Röntgen's X-ray generator, which you can see in the Deutsche Museum in Munich. Now, of course, the modern in-house generators look different, but they work on the same physical principle. Now, the synchrotrons, in the synchrotrons, X-rays are generated by a very different mechanism, and they are millions of times more strong than what you get with a conventional X-ray generator. So this is a modern X-ray diffraction experiment, a protein crystal in front of a synchrotron beamline. So you collect millions of data within a few minutes. Now I skip the other possibilities that the modern technology now offers. One for protein structure determination. One is that synchrotron radiation you can tune, you can filter out a very narrow X-ray bandwidth, and making use of that for making use of the anomalous absorption properties for analysis of, let's say, metals in proteins. Now, in this way, we discovered in a large protein complex that this is copper, very unexpected by chemical means that was not possible, but not only for analysis, but also you can use it for phase determination. Another important aspect is that with the growing knowledge of protein structures, you can make use of that information. You can use a related protein structure, related by comparing amino acid sequences, for instance, to analyze the crystal structure of a related protein. Now this is, you do have a model, and what you then have is you reduce the problem to a 6-dimensional search with 3 orientational parameters and 3 translational parameters, which you can solve. So this is actually the most frequently used protein crystallographic structure determination method that we use right now. And we have developed refinement. This is the original electron density that you get with experimental data. You see there are breaks in the electron density, so obviously problems with measurement, phase determination. Now what we do then is including information that we have from other sources, namely the exact geometry of the protein constituents, the amino acids. We know precisely what their atomic structure is, and that information we can include. So it's in a way, the crystallographer's way of achieving super resolution that I mentioned in optical microscopy. Well, we also use averaging long before the electron microscopists made use of that. Now, often proteins are symmetrical oligomers. For instance, this is a pentameric molecule, and the original electron density looks like this, really very bad. But we know from other information that it is pentamer, and then we can impose on this electron density the pentameric rotational symmetry, and by applying this in cycles, we can get a high resolution electron density and a good model. So this is our way of symmetry averaging. The electron microscopists have then copied later and use to very good advantage now. Well, this is a question that has to do with with several subjects discussed in the biointeratomics conference. Now, what can we do about molecular dynamics by X-ray crystallography? In principle, little. Crystals are prototypically rigid objects, so there is no motion in them, very little motion. But what we can do is trying to stabilize a particular protein in a certain conformation that is, for instance, with substrate or ligand bound or with inhibitor bound, and then crystallizing it and analyzing the crystal structure, and then comparing these different crystal forms and molecular forms that we see. Of course, this does not give us any information. It gives us information about the limiting states. It does not give us any information about kinetics or energies or the trajectories of these transitions. These are two examples that we analyzed some time ago. Quite massive motion that we can see in these molecular complexes. Now, in some cases, large proteins, there is limited motion of just a part of the protein. This is, for instance, the active site of CO dehydrogenase, to which I will come back if there's time later. So in that case, the protein could be analyzed in oxidized, reduced state, in inhibitor-bound states, and the crystals tolerated these changes, so we could use the same crystal form for the analysis and just look at the active site and see the motion there. Again, it's just limiting states that we see fixed, no way to say anything about energetics and kinetics. Well, physics in biology, a few slides about photosynthesis, which is the process on which we all higher life lives. This, and the only process, biological process that we see from space, if we look down on Earth, this is winter, this is spring, this is summer, and this is autumn. Now it's quite curious that Andalusia is always brown, but it is not. It's very green. So there must be something wrong in this satellite photograph. Well, there are two principal functions. One is in photosynthesis, one is light collection, and we do have specific components that do collect the light, which are, and the light or the light energy then transferred to the photocell. So we do have light collectors and we do have the photocell. And just a few pictures about what we did here. Now these are these enormous light collecting elements in cyanobacteria called phycobilisomes. These are huge aggregates, much too large and too heterogeneous to crystallize. But we can isolate the main components of these phycobilisomes. These are three components, beautifully and differently colored. So the terminal red components, then the deep blue middle components, and the light blue inner components, which are in contact with the photosystem or the reaction center, that is the photocell. So we crystallize these individual components. By the way, we had yesterday about phytochrome and the chromophore there, which is identical to the chromophore that we have in these proteins. Now, the chromophore in the phycobilisomes does not undergo any structural change upon illumination, and it should not. It should really conserve the light energy and conduct it on to the photocell. Now, there is, when we saw this structure for the first time, then a very simple principle of its function was immediately obvious, because the outer components do have 15 chromophores in this trimeric, alpha-beta trimeric structure, while the inner component has only 6. So the light is absorbed by many components and is then concentrated when the light energy flows down these rods into the APC component, which contacts the reaction center. And this is the reaction center. Miguel showed it already. This part is the membrane embedded part, consisting of 2 helical subunits. It also holds the chlorophyll system, and particularly important is a pair of chlorophyll, the special pair, which is the component with the lowest lying energies. So all the light energy, the excitation energy that flows into the system, then gathers, is collected here, excites this pair of chlorophylls, which then eject an electron, which travels down very quickly in picosecond to reduce a quinone. This is the primary reaction of photosynthesis. Well, interesting aspect of evolution. Now, this is the reaction center from bacteria that we analyzed, and 20 years later, the photosystem 2 from photosynthetic bacteria and then later also of plants was determined, which is much larger, has 19 subunits compared to 4 subunits. But the inner 2 subunits, which harbor the chlorophylls, are identical. So the heart of the machine, the working part of the machine, is conserved in evolution, and then more and more regulatory subunits have been added during evolution, from the primitive bacterial photocell to the plant photosystem, to a wonderful example of how evolution works, conserving the essential part that was shown to work properly, and then adding more and more regulatory subunits. Well, I skip this, but chemistry and structural biology, and come to a few words about applications in medicine. Now, I was interested in that aspect early on, in the beginning 70s, also by interactions with Big Pharma, which I had at that time. And I first focused on a particular class of proteins, which are the proteolytic enzymes. These are the proteins that cleave other proteins. So it's happening in our digestive tract, and you all know about trypsin or chymotrypsin as the major digestive enzymes. But when one looks at the genes of humans or of mouse, one finds up to 600 different proteolytic enzymes. How comes? As I said, it's a very simple reaction, proteolysis, cleavage of a peptide bond. Now, why do we need so many? Now, we need so many different proteases because proteolysis, and in particular limited proteolysis, has a regulatory role. So what we were interested at that early time was to find out how proteases are regulated, because unregulated they are really dangerous, because they would work inside cells or outside cells and digest the essential components of a living organism. So what this cartoon here shows, the different modes of regulation of protease activity in nature. Now, the simplest one you see here. Now, this would be the enzyme, this would be the substrate binding site, and there are then proteinaceous inhibitors around that bind very strongly, very tightly to the protease and, of course, inhibit its function. Very simple. Now, this is actually the first mode of inhibition that we found, again, by crystallography. This is the complex of the digestive enzyme trypsin with its natural inhibitor, which is made for its target. You see the surfaces are quite complex, quite irregular, but they are perfectly made for each other. There is no structural change when we compare the complex structure with that of the individual components. They are really perfectly adapted. Now, we found this principle then in all the other major classes of proteases, so the papain-like proteases, the metalloproteinases. So they all have their natural inhibitors which bind in a substrate-like way to the enzyme very specifically. So lock and key inhibition by natural inhibitors in all major classes of proteinases. So this came out from many, many crystal structural studies. Now, nature makes use of that as well. These blood-sucking animals, that's the leech, that's the blood-sucking bug, and this is the tick, they do have, they are actually, the leech in particular, bags full of protease inhibitors. Now, in this case, thrombin inhibitors. You know that thrombin is the major enzyme of blood coagulation, and the leech eats must be kept liquid in order to make it digestible for the leech. So they have very powerful thrombin inhibitors, which again then are used in medicine either directly or in variants. Well, now I see that we are somewhat late, Miguel. I'm thinking about what to skip. So the major project that I'm following in the last 15 years are these large proteolytic enzymes that are in cells. Now they showed a special kind of regulation. I spoke about the simple regulation in the trypsin inhibitor case. We found others, but that was novel what we found in these intracellular proteases, which are called proteasomes. They do have their active sites inside the particle, and the access is blocked by the entry ports, which are closed. So in that state, the protease is latent. So the ports have to be opened in order to activate the molecule. So that is what we wanted to explore. Now, what is the proteasome? It's a very big proteolytic enzyme consisting of 28 subunits, and it plays the role of an executioner in the ubiquitin pathway. Now, this is a pathway that is required, for instance, in cell signaling, because proteins that should be short-lived, signaling the cell cycle, they are marked with a polyubiquitin chain, and this then is the signal for the proteasome to be bound and leading then to degradation of this signaling molecule. So this is one function, the executioner of the ubiquitin pathway. The other is that it is the waste cleaner. So our cells are actually full of damaged proteins which have to be removed quite efficiently. Again, this is done by this large protease, the proteasome, and if these are from foreign sources, so let's say a virally infected cell, then the peptides that the proteasome generates are then antigenic, and they are transported to the cell surface in complex with MHC class I molecules, triggering the T-cell immune response. Now, the first structure that we analyzed was that of a Archaebacterium. Shows already the basic architecture consisting of 28 subunits, but only two different ones, the alpha and the beta, so obviously the molecule has symmetry. And then a few years later, we looked at the eukaryotic proteasome, found the same architecture in principle, but now here all the alphas and all the betas are different. Again, an example of evolution. So maintaining the basic successful construction and then varying the subunits to generate regulatory opportunities and different specificities. So that's the same that I mentioned with the photosynthetic reaction center. Now, the proteasome is an essential molecule in cells, and therefore it was a big surprise for the community to find out by the work of a small American group that the proteasome is a drug target for blood cancer, in particular multiple myeloma. This was a big surprise. Of course, they had the structure that we had published in their hands and designed this little molecule, which is a boronic acid, according to the structure that we had deposited. Now, it was a noble strategy and actually very successful and very helpful for many, many patients. Now, also the economic success by this American company then spurred an intense search in chemical libraries, in natural compound libraries for other proteasome inhibitors that might have less toxic side effects. And I'll come back to that in a minute. Now, many of these discovered around the world were sent to us with the request to analyze their binding sites to the proteasome. You see these fantastic different chemistries. These are lactones. This is a beta-epoxy these are the boronic acids. This is an unsaturated amide group. So all you find in nature, in fungi or in bacteria, which make these molecules in order to inhibit the proteasome for purposes that is still unknown. Anyway, I mean, we are interested in these different chemical entities. We were involved in the discovery of a few. This is collaboration with a plant biologist in Zurich who found that this bean plant pathogen makes and requires a virulence factor which they isolated, calling it the syringolin. Now we found out what it does is inhibiting the plant proteasome. So the pathogenic bacterium kills or causes apoptosis by inhibiting the plant proteasome, which then leads to the accumulation of polyubiquitinated cyclin B1, as you see here. Now, this is the crystallography showing this molecule bound to the proteasome. Well, I skip this. No, I don't skip. Well, the problem with proteasome inhibition is the toxicity. Now it was known, and we followed that up, that under an immune stimulus, immune cells produce a slightly different kind of proteasome. Very similar to the constitutive proteasome, but it has a somewhat different cleavage specificity, and it works faster. And of course, we wanted to understand that. That was one aspect of our interest in that. The other one was that we could expect that specific inhibition of the immune proteasome might avoid the toxicity of the inhibition of the constitutive proteasome, one, and second, then it might offer a new strategy against autoimmune disorders. So we embarked on designing and making specific immune proteasome inhibitors. Now, this is already work that is far outside of what an academic laboratory can do. Now, the Max Planck Society has set up what a daughter that is called Lead Discovery Center, and they accept ideas from academic institutions to develop them further to a stage that becomes interesting for big pharma to license or to start a strategic cooperation. So I suggested the proteasome, the immune proteasome, and they took it up. We continued to work, of course, crystallographically on the immune proteasome. We found out, for instance, that the immune proteasome does not undergo structure change that we see in the constitutive proteasome upon peptidic ligand binding. This was very important. We did molecular dynamics as well, which confirmed the experimental results. And now the last 5 minutes, a few words about real translation, namely translation into business. Because, I mean, I always had a good collaboration with big pharma, big exchange doctoral students, but then I thought we should make use of the vast knowledge that we had accumulated, the expertise, and found a company that offers services to big pharma. For a fee, of course. They have to make a living on it. So we founded a company, 2 of us. Thorsten Neufeind was a former doctoral student. I acted as co-founder and advisor. I never had a role in the business. This is not what I like to do. Now, the company grew to now about 70 scientists. They have their own laboratory building in the Munich area. And this is what they do. They, for customers, work protein production, assay development, structure analysis. They have a very large collection of ready-to-go crystal structures of medically, of pharma important drugs, such that if a company comes and would like to know how their new ligand binds to a target, they will get an answer in a month or so, because all the processes have been set up. Well, they also offer thermodynamic profiling. This was a question in the bioatomic conference, namely the importance of the ligand target lifetime, in particular the dissociation rate. It turns out that this is probably as important, or perhaps even more important than the affinity, namely long lifetime and long dissociation lifetime. Well, now this is the customers the company has. It's a list of most of the prominent pharma companies. Now, the second company was founded 2003 again by two former doctoral students. And what this title says, that founded in 2003, and it made the investors happy, and it made the lawyers happy, and the founders somewhat less happy, but not unhappy. So this takes me a few minutes to go through that story. Now, the story actually began a long time back in 1976, when we analyzed the first intact antibody crystal structure, which is now textbook knowledge. It's this big protein that recognizes the tips of these FAB arms, as they are called, antigen. And this is the stem part that you see here. Now, the antibody molecule is the central mediator, both of the humoral response and of the cellular response. Now, we were mainly interested in the cellular response. What does this mean? This is an antigen, opsonized, as it is called, with specific antibodies. Now, this complex then binds to receptors which recognize the stem part of the antibody. And there are two different types of receptors. One that stimulates the immune cell, and one that inhibits the immune cell. Now, so what we did with our tools, we looked at the receptor and its complex with the Fc part, and you see this. You see that there is some motion in both molecules. And then we thought, what can we do with that? What we would like to do in the case of an autoimmune disease to inhibit the immune response. And we thought that we could achieve this by using soluble Fc receptor, easily to be made. Now this then would bind in solution to the antibodies bound to the antigen, which then no longer can bind to the cellular Fc receptor and therefore stop the immune response. So that was the idea. Another idea was that we could make a specific antibody against the Fc receptor, which we did, and it was then found that when we make an antibody that does not interfere with the receptor antibody binding, then this would have an inhibitory effect. Again, there was crystallography of this ternary complex done. So these were the two strategies. A fascinating finding recently was published by Roche. Now they wanted the opposite. They wanted the enhancement of the cellular immune effector functions, and they found out for, let's say, the higher efficacy of therapeutic antibodies, that is antibodies in cancer therapy, and they found out that if they use antibodies that do not carry a fucose, that they bind much stronger to the receptor. So they made then defucosylated antibodies, therapeutic antibodies, and found a 100-fold enhancement of the cellular immune effector functions. So we wanted to reduce, to inhibit the immune effector functions. Now in that case, one wanted to enhance the immune effector functions. Both you can do by structure-based design and then experiment. Well, so we went on then with our soluble receptor as an antagonist in animal models of some autoimmune diseases. And then, of course, this is always a costly process. So these were 15 to 20 people working in the company. So you needed investors. There was no income at all. Investors were still happy, but then they were very happy with the final outcome beginning of last year when a big American company then bought this Suprimol, I forgot to mention their name, for a big sum of money. Therefore, I say investors became happy. One of the investors, by the way, was the Max Planck Society, acting not only as my institute, but also as an investor. Now the founders were happy because the project now under the umbrella of Big Pharma continues. Well, with this I end, show Munich. This is the old university in Munich, in the center of Munich. And this is where Laue Röntgen is professor of experimental physics. Laue is as professor of theoretical physics worked and began more than 100 years ago with protein X-ray crystallography, which developed into protein crystallography. Thank you.
Thank you, Dr. Huber, for your excellent lecture. Then we will proceed to impose the medal of the institution to the new academician. En nombre de Su Majestad el Rey Don Felipe VI y por el poder que me otorga dentro de esta academia, tengo el honor de nombrarle académico de honor de esta Real Academia Sevillana de Ciencias. This is the oath or promise. Yes. You have to. You can use the microphone. You can go to the microphone.
Well, this document reads Oath for the Position of Academician of Honor. I swear by my conscience and honor to be faithful to the obligations of Academician of Honor of the Royal Academy of Sciences of Seville. Now it comes, with loyalty to His Majesty the King, and to observe and enforce the Spanish Constitution as a fundamental state norm and the Statute of Andalusia.
Members of our academy and the members of other academies of Seville. They are in the three first rows here and in the first row there. But you could be...
Well, I start here.
Royal Academies.
Ahora llamamos. Claro que no.
La academia está regida Uy, será por la sala.
Sí, sí, ya está. Decirle... Aquí sí.
Yeah.
Thank you very much. Then you may sit down there.
You sit over there with the convention.
We continue. Excelentísimo señor consejero de Economía y Conocimiento de la Junta de Andalucía, excelentísimo señor presidente del Instituto de Academias de Andalucía, excelentísima señora vicerrectora de Internacionalización, dear fellows, ladies and gentlemen, today we have accepted a new academician of honor in our academy. According to Article 17 of our bylaws, the academicians of honor will be those persons well renowned in the field of sciences designated by the Academy. The maximum number of honors academicians that our Academy can designate is 9, of which at least 5 will be of Spanish nationality. At present, we have only 5 academicians of honor, and this indicates the zeal of our Academy in the selection of these scholars. With respect to the non-Spanish honors academicians, we have only 2, being the other Jean-Marie Leng, Nobel Prize in Chemistry in 1987. This way, our institution recognizes the close link established by Dr. Huber with the Andalusian capital, where he comes frequently to impart lectures, conferences, or to monitor young PhD students, including those of the Research Center Cartuja Island, CIC Cartuja, Mixed Center of the Spanish Higher Council of Scientific Research, Junta de Andalucía, and University of Seville. I remember his presence in our academy in a symposium organized with Fundación Areces. For this reason and his outstanding merits, Dr. Huber was elected unanimously as academician of this Royal Academy. His introductory speech entitled New Ways of Vision, Beauty and Fitness for Purpose of Proteins and My Experience with Translation into Medicine has treated one of the main lines of research that has marked his career, the knowledge of proteins and the possibilities they offer in the treatment of various diseases. The intervention has been preceded by a laudatio of the Vice President Miguel Ángel de la Rosa. His achievements have been reminded in the laudatio. The biggest boost of his career arrived in the 80s. Dr. Huber focused on biological photosynthesis and managed to determine the three-dimensional structure of proteins, which was of paramount importance to understand the conversion of light energy into chemical energy. He was elected a foreign member of the Royal Society of London in 1999. He is universally well known as he received the Nobel Prize in Chemistry together with his co-workers Johann Weizsäcker and Helmut Mitchell in 1988 for the determination of the three-dimensional structure of a photosynthetic reaction center. The development of methods of protein crystallography has been in the focus of his laboratory's work from the beginning and led to the development of refinement in protein crystallography. His methods and programs are in use in many laboratories in the world today. Owing to all that, it is an honor for our Academy to receive Dr. Huber as honors member of our Academy. Welcome, Dr. Huber. A continuación tiene la palabra la señora doña Carmen Vargas Macías, vicerrectora de Internacionalización de la Universidad de Sevilla.
Thank you very much. President and members of the Academy, Professor Huber, Councillor Antonio Ramírez de Arellano, members of the University of Seville Governing Board, members of the US community, ladies and gentlemen. Well, first of all, I would like to express one more time the gratitude of the University of Seville, which today I represent, to the Academy of Sciences of Seville for choosing the Paraninfo, our main hall, for celebrating the induction ceremony of the distinguished scientist and Nobel Prize laureate, Dr. Huber. Our sincere congratulations to the new Academy member, to whom I deeply admired, being myself a university teacher and also a molecular microbiologist. Our rector used to say that the Academy of Sciences of Seville is, among all Andalusia academies, the one having the strongest university hallmark. This is because of the tight link with the University of Seville. This is because many Academy members are professors of the US. And this is also because the kind of activities that the Academy implements. In our view, one of the main roles of the academies is to serve as a nexus between the knowledge generators, the scientists, and the society. At the same time, they collaborate with the universities and research centers to boost research at the international level, not to say the promotion and recognition of young talents. Seminars, research awards, symposia, or conference series are just few examples of the intense academy life. The University of Seville has more than 500 years of history. We are old, but not tired. Despite the financial and structural crisis of the last years, the US keeps an intense activity devoted to research and knowledge transfer. At the international level, the University of Seville is well positioned in the main world university rankings, such as the Shanghai, the QS, or the THE rankings. At the national level, the US ranks 9 in terms of scientific production and is the best performing when it comes to number of registered patents. Committed with the regional growth, the US is the first university in Andalusia in getting funds from the European Commission framework programs. Together with the University of Malaga, we led the International Campus of Excellence, Andalusia Tech. This is an ambitious and long-lasting project where universities and other stakeholders join forces around 6 poles of excellence, being one of them biotechnology for a healthy society, a specialization sector which is very close to the Academy of Sciences. Professor Robert Huber is an old friend of the University of Seville. He visited us many times. For instance, in 2009, after a tour through our general research services, he gave a conference entitled Molecular Machines for Protein Degradation Inside Cells at the Faculty of Chemistry Auditorium. However, as it has been said, this was not the first time that we were fortunate having him with us. Professor Huber joined the US at May 2006 as Honorary Professor of the Doctoral Program on Structure and Function of Proteins. This was an outstanding and highly recognized PhD program shared by the Department of Plant Biochemistry and Molecular Biology of the University of Seville, the University Autónoma of Madrid, of Barcelona, the University of Zaragoza, and the Institute of Physical Chemistry Rocasolano, belonging to the Spanish National Research Council. We would like very much to recruit again Professor Huber for collaborating in some of our postgraduate courses. A nice example is our renewed master course on molecular genetics and biotechnology, which offers a very specialized curriculum to students coming from the fields of biological and health sciences. This participation will illustrate again the complicity between academy and the university, with two academy members, Professors Robert Huber and Miguel Ángel de la Rosa, involved in a master of the University of Seville. Molecular architects. In this way, Professor Huber describes Professor de la Rosa, who is academic, professor of biochemistry and molecular biology of the US, and director of the research center SIC Cartuja, one of the joint centers between the University of Seville and the National Research Council. Just to finalize, congratulations to the Emeritus Professor, José Luis de Justo Alpañez, President of the Royal Academy of Sciences of Seville, for the impeccable, the perfect organization of this ceremony, and once again to Professor Huber for becoming a member of this prestigious academy. Thank you very much.
Don Antonio Ramírez de Arellano López, consejero de Economía y Conocimiento de la Junta de Andalucía.
Thank you, Mr. President of the Academy, President of the Institute of Academies of Andalusia, Vice Rectors, Academy members, Professor de la Rosa, Professor Huber, ladies and gentlemen. I also want to add my wishes of a quick recovery of the rector of his domestic accident. I was really surprised, it was a nice surprise to see the picture that Professor de la Rosa just showed. We were 12 years younger than today, and it's an interesting picture because in addition to the present rector of the university himself, that's now the director of the SIC Cartuja, Professor Huber, that everybody sees is the same as today. And in addition to that, I am now the regional minister of Science and Economy, and also Manuel García León, today the Director General of Research and Technology or Knowledge Transfer, that is in my team in the regional ministry. So it's a nice picture. I still recall the nice lunch we had after that picture, and still remember the good conversation with Professor Huber that really impressed me with his commitment to come here to Seville and to expand his views of science and how he helped us in that time. It is always good news when a family adds a new member, and it's even more so when the new family brings the scientific and human stature of Robert Huber. Professor, may these words serve as a warm welcome and an expression of gratitude for sharing with us your experience and your knowledge. Professor de la Rosa has made a perfect journey through the life and curriculum of Professor Huber. Little remains to add in that matter. Therefore, I would like to take a minute to underline merits of Professor Huber, to which, in my opinion, we should all aspire. First, your generosity in sharing and strengthening ties internationally. Our new honorary member is renowned by his scientific work, awarded, of course, with the Nobel Prize, but adds close ties that bind him to this city and her scientific community. They are already a good number, the visits Professor Huber has paid to Seville to lecture, teach, or support our young talents. A good reminder that as scientists, our goals transcend borders. The path to excellence does not wind around nationalities. This is why from Andalusia we look outside to the entire world to find our references. We have come a long way in the last 40 years. By reaching out to good friends like Professor Huber, we have consolidated our integration into international networks of science and innovation, searching for synergies to participate and, of course, lead frontier-level initiatives. I also want to highlight Professor Huber's defense of basic science. Every achievement, every advance, every new application is only possible by the previous work of thousands of scientists. In these times, scientists felt increasingly hard-pressed to achieve some useful so-called results. This is normal. Many leaders have turned to science for answers, especially as the crisis became longer and harder. We must remind the society, and in particular political leaders, that if we look further, it's because we have traveled on the shoulders of the giants, as Newton would say. If we really aspire to be leaders in innovation, we cannot reduce our investment in the most fundamental research. Professor Huber's commitment to the basic science has been also linked to his interest in addressing social challenges. His curriculum is well described in this matter. But at the same time, Professor Huber knows about application. As he has shown, he's co-founder of a couple of companies that are successful entrepreneurial experiences. But let me introduce some ideas on economy too, the other branch of my regional ministry. We need a healthy economy, a science-driven economy, a knowledge-based economy that provides enough wealth and resources to fulfill the social goal established in our Constitution that now Professor Huber has sworn to respect, and also a well-established European tradition. We want to achieve welfare and social cohesion. No one should be left behind. In Andalusia, we are committed to the policy that offers citizens the opportunity to give the best of themselves, fostering talent in an equal opportunity society. Young people is crucial to achieve this goal. Professor Huber also defends young people. During a visit to Spain a couple of years ago, he stated clearly, I recall that, when after the crisis we're turned back to young scientists, they will no longer be working on this. Science, driving force, is a clever combination of the experience of the senior and the will and grace of the young. It is urgent to reverse the absurd direction of the matters. Young scientists are not asking for money, even though they are entitled to have a good conditions. They are demanding a future. Let us offer them something to believe in. And I am concluding now. In addition to his words, we can all learn of Professor Huber's actions, his career, and his ways in such a beautiful job as research. Joining as an honorary member of the Royal Academy is an opportunity to do so. I cannot think of a better example for our young scientists. Thanks, Professor Huber, for accepting this new membership, and thanks to the Royal Academy of Sciences of Seville for inviting me to share this moment. Siguiendo la instrucción del señor presidente, levanto la sesión. The session is adjourned.
So just a minute for the foreigners, for the participants in biointeractomics workshop. Now there will be a cocktail. Just leave in the room on the right. So don't leave the building.